been having issues with Zoom, just like taking a little longer to open than it has in the past, or is that, does anyone know? Yeah. Test. Okay. All right, good morning. Let's see. At home, Austin, can you hear me okay? See me okay? Share screen is good? Okay. All right, everyone. I'm going to pass around this sign-in sheet. Remember, this is just so I can keep track of who is here. You did this last time. Let's just flip it over and just start a new column right here. You mind? You don't mind? Okay. Any questions before we begin today's stuff? Yeah. It's 9 a.m. is killing you, isn't it? Yeah. Okay. All right. So last time we were talking about the definite integral, right? And I had brought up this idea of, oh, come on. Where'd it go? Hold on. I've got a window hidden behind another window somewhere. Can't find it. Freaking technology, come on. I've got a little hourglass here, just hang tight. We'll see what happens there. So last time we were talking about the definite integral, right? And the main idea was that now what we can do is find areas under curves. And we proved the area of a circle is pi r squared. But this was the main thing right here, that what we had been doing before was the indefinite integral. So we would use this notation. And at the time we used it, we didn't realize what this symbol really was going to stand for later. We just said, okay, that's notation. It just meant go find the antiderivative, right? And so you get this family of functions. And now what we've looked at is that if we add two numbers here, now this thing has some meaning, and it has geometric meaning. And that geometric meaning is going to be vital to when we move into the next chapter and we do applications. So, you know, this integral sign represented the idea that we're going to do an infinite sum of f of x times dx. That was the height and width of all these little rectangles underneath a curve. And then the two numbers were just where we start and where we stop, right? So what I'd like to do, if I can get this to open, I don't know why this is not opening. I'm just going to have to close this program. Let me do this. I've got to kill off Mathematica here. Okay. Let's see if it comes back or not. There it is. Okay, so what I want to do now is establish some. Let's start with an example. How about we do that? Let's do an example just to kind of get our feet wet again. And let's do this one. Let's do the integral. Let's go from 0 to 2 pi, and let's just do sine x. Okay. So geometrically, what this is saying is that we need to take a look at the sine function, which are experienced from Cal 1 and pre-Cal. We know that the sine function looks like this, has a period of 2 pi, right? So here pi is in the middle, and the amplitude is 1. And so what we're interested in finding here is the area, right? The area under this curve. So we're trying to figure out, what's this area and this area together. That's what this is going to give us, right? This is the answer to this will give us that yellow area. So let's just run through it. First thing we do is we ask ourselves, can we find the antiderivative of sine of x? Of course we can, right? What is the antiderivative of that? Careful.
Negative cosine x.
Negative cosine x. So we have negative cosine x. We write that down. Then we put the evaluation bar. And we put our two limits of integration. I said limits of integration. That's terminology we established last time. So I put those two there. So that's just kind of a placeholder for us to put the antiderivative, put our two limits of integration. Now what we do is we evaluate that antiderivative at the two endpoints, always starting with 2 pi first. So negative cosine of 2 pi. And then we'll subtract from that negative cosine of 0. What is cosine of 2 pi?
1.
1 pi. You're thinking pi. So all the way around, right? So
Yeah.
now it will be -1 because the negative in front of it. So this will be -1 minus, and then again, cosine of 0 is also 1. So we have -1 again. And so when you put those together, you get -1 plus 1, and you get 0. Well, it kind of makes sense, but doesn't make sense if you think about this, right? Because the yellow area here in the first little, we call that the first arc of sine. That yellow area is somehow being counted as positive, and then the area below the x-axis is being counted as negative, right? That's what it appears is happening here. So it makes sense that the answer is 0. Now, why is it counting it as negative? Because I thought all areas had to be positive. Why is this integral sign counting that second arc is negative? And this is where the geometry comes into play, that you understand how the formula works. So if we look at this, think about again what the whole idea of those Riemann sums was. You were going to take all these rectangles in here, right? All these rectangles. You're going to fill this up with an infinite number of rectangles. And each of these rectangles, the way you were going to calculate the area was by saying the width of it was this little infinitesimal dx, right? That's how wide it was. And the height of the rectangle was the function's value, right? So if you multiply those two numbers, if we're in this first region here in yellow, if we're here, the width's going to be positive and the height's going to be positive. When you multiply two positive numbers, you'll get a positive answer, right? So it's going to count all of this as positive. But when we get to the other region here, and we start filling this with rectangles, when you look at that, the width is still dx. So you still have a positive number, right? But the function's value, f of x, is negative because your function is below the x-axis. So even though we know the height should be measured positive, the integral doesn't know. It just looks at the sign of the function, the value of the function at that point. So it's going to count it as negative. And then, of course, a positive times a negative is negative. So it's counting all that area over there as negative. And so since there's some symmetry here, right, they would cancel each other out. Does that make sense to everyone? So the integral doesn't really give you like the true area. It almost gives you, what would you call that? Like a net area? Because it counts things that are above the x-axis as positive and things that are below as negative, right? So it's kind of like a bill, or an invoice. Anything that's positive, it's counted. Anything that's negative, taken out. So it gives you like a net total at the end, which is good and bad. I mean, that can be bad, right? I mean, what if I wanted to know this true area? How could I do that?
Absolute values.
What's that? Yeah, do part of it. Why don't we just do this piece, the first little piece? So instead of going from 0 to 2 pi, why don't we go from 0 to pi, right? And then maybe double the answer because of the symmetry. Or we could also go from pi to 2 pi. We know that answer would be negative, but then just change it to positive. Now I heard absolute value. We could do the absolute value also. The only problem is the integral of the absolute value is not as easy, right? If we put absolute value around the sine x like this, then that antiderivative is not, we actually haven't even talked about what the antiderivative of the absolute value of something is, have we? So this will be, now I'm not sure if that's what you meant at home. You might have just meant take the absolute value of the answers, put them together. In that case, yes. So I guess, you know, I guess the moral story here is we have to be a little careful to not trust that the integral is going to give us the answer, and that we have to investigate this a little more if we truly want to know what's going on. So understanding the graph of what we're doing is important, right? Okay, so if I wanted to do just this arc right here, let's just do that real fast. If I were to change it, and let's just do the integral from 0 to pi of sine x dx, the only thing that changes is our limits of integration. And then when we plug in, we'll be able to find that. So we get negative cosine of pi, and then we get negative cosine of 0. Y'all understand all I'm doing? The only difference is the pi instead of 2 pi. So cosine of pi now is -1. So we're going to have -1 in that first parenthesis. And then minus, we already said that this was going to turn out to be -1. So your answer is 1 plus 1, which is 2. I've always found that to be very weird. I don't know about you, but I find it very, very odd that the area underneath the first arc of sine, which is not, there's no straight lines here, right? It's all curved, it's weird shape, that the area of that is a nice number. It's 2. You would think it'd be something odd, right? Like something strange, maybe something involving pi. Since circles, the area has pi in there, but it's not. It's just 2. It's a nice number. It's weird. That means the area of this is also 2 if you look at it as like a true area. So the total area of these together should be 4. Understood? Now, if you're asked a problem like this on a test, your answer is going to be 0. Okay, that is the correct answer, 0. But if you're asked, if someone gives you a picture of this and says, hey, what's the area of these together? Then your answer would need to be 4. Understand the difference? It all depends on the context of the problem. Okay, so let's now talk about these properties. So we've introduced the idea of the definite integral. Okay, this is the formula for it, right? This is what we talked about last class. And now we want to talk about some properties. So the first property says that if you do the integral from a to a of any function, your answer is 0. So does that make sense to you why that would be 0? If you're going from a to a, then you're looking at, hold on, I need to open up one more program here. So for this one, hold on, I haven't used this mouse in a while. There we go. Okay, so if we're looking at this first property, it means you're starting at A, right? And then you're also ending at A. So the function really above that is a single point. And you're trying to find the area underneath that. Well, the area is just a straight line down. And straight lines don't have areas. So your area should be 0. Is that pretty simple idea? Okay. The second property says that if you do the integral and you go from A to B, all right, that means you're going to have, the idea here is that you're going from A to B, and you have some function here that whatever this area is, it's equal to the negative of the area under the same function going from B to A. So in other words, if you reverse the direction, then you get an opposite answer. And the reason goes again back to the idea of dx. If we were to look at the rectangle in here, right? We know that the height of the rectangle is f of x. The width is dx, right? It's how wide this thing is. Well, if we're moving from left to right, then the width of that, we're going to measure it as being the right endpoint minus the left endpoint. That will always be a positive number. Does that make sense? But if we go from right to left, then when we look at the difference, that will be a negative number because we'll be taking a number on the left, which is smaller than the number on the right, and then we'll subtract them. So we'll get a little negative. So dx will be negative. Everything else will be the same. And so when we compute this little area, it'll be the opposite of what we got the other way. That's useful because sometimes we do like to change the order of integration. And when we do that, we just need to realize that it changes the answer to the opposite. All right. The next property, trying to remember all my buttons here. Nope, that's not it. What is my clear button? This one. Yeah. Okay. All right. So this one says the integral from a to b of k dx equals k times b minus a, where k is a constant. So this I have a little picture for. Imagine that you have a function here, and this function f of x is some constant k. So here it looks like k is 2, but I'll just say that it's k. So it's just a flat function, right? If you want to integrate anywhere from a to b, doesn't matter where you start, doesn't matter where you stop. If you want to know this area, all it's going to be, the total area is just however tall it is, right, k, times however wide it is, which will be b minus a. Right, that's how wide this interval is, b minus a, and then the height of the whole thing is k. See, this is an interesting problem because it's constant. It's constant, it's a rectangle. If it's a rectangle, we can find the area easily. Width times height, we're done. Does that make sense? You know? As a specific example, just so you can kind of see this in action, if we were to do the integral from 5 to 10 of 7 dx, for some reason, this seems very narrow. Let's see if that's too thick. That's better. Okay, so if we do this, we realize that 7 is a constant, right? And so all I have to do is take 7, multiply that times the 10 minus the 5. And you'd get what, 7 times 5, which is 35. Right? You don't have to do any antiderivatives here if it's a constant function. Now, what if you did do the antiderivative? Would you get the same answer? I think so. What's the antiderivative of 7? 7x. So you would take 7x, evaluate that from 5 to 10, and then you plug in 10, you plug in 5. Let's see, if we plug 10 in here, 7 times 10 is 70. We plug in 5, we get 7 times 5 is 35, and 70 minus 35 is 35. So it's not like you would go wrong if you did it the other way. It's just a nice property. Questions? Okay, next one. Property 4. This is a property that I think makes sense. It makes sense because of what we learned in Cal 1. In Cal 1, we learned that when we take a derivative, constants come for the ride. And even when we were doing antiderivatives before, weren't we always pulling constants out of the integral? Same idea. If you have a constant inside, you can always just pull that constant on the outside and then find the area here. Property 5, this again, I think is pretty intuitive. If your function's greater than or equal to 0, that means if your graph of your function is above the x-axis, now it can be on the x-axis, but as long as it's above and it never goes down, right, below the x-axis, then the area underneath it, right, this is the area underneath the curve, that has to be a positive number, right? If your function's always above the x-axis or never below it, then no matter what, your area is going to have to be either positive or 0. It could be 0 if the function is flat on the x-axis, but that'd be boring. The second property is the other way. If your function is not above the x-axis, right, below, then your area underneath it's got to be negative also. Property 7 is a property that we're going to use actually in a little while. It says that if you look at three numbers, A, C, and B, where they are in this order, A is smaller than C, which is smaller than B, then the integral from A to B is equal to the integral from A to C plus the integral from B to C. So what is that saying? Just let me show you a picture here. It's just saying that if you have an integral and you go from A to B, okay, an integral goes from A to B. So A is smaller than B, and C is any number in between them. So I'm just going to pick some number here in between, okay? Then the total area of the whole thing should be the area of the green and the yellow together, right? Added up. Well, the area of the green is this integral, and the area of this is this one. I need to come back on screen a little bit there. Yeah. I don't think I'll be able to fix that, but yeah. Okay. I hope that makes sense. The integral from A to C, take that answer, the area there, add that to the integral from C to B. Those two together are equivalent to the area from A all the way to B. Is that intuitive also? These properties are just to make sure we understand we can do this. So when we do it, you can never take anything on complete faith or for granted. You have to establish the rule. Okay, this one is cool. Property 8. If f is an even function, what does it mean to be even? Think about geometrically. What do even functions look like? They have a very special property when you graph them. Even functions.
Symmetric.
They're symmetric to which axis?
The y.
The y-axis. They're symmetric to the y-axis. So all even functions are symmetric to the y-axis. So if you reflect them over the y, they'll land on top of themselves. So we'll talk about the property. Here's an example. Here's an example of an even function, the blue. Notice that if I take this blue function and reflect it over the y-axis, it'll land right on top of itself, right? That is what even functions look like. This property says that if we integrate from negative a to positive a, now it's important, it's not saying from a to b, it's saying from negative a to a, right? If we want to find that area from negative a to a, all we have to do is really look at it from zero to a. So you can ignore this, find that area, whatever that is together, and double the answer. Because you know that that's what it is on the other side also, right? So that's what this says. Double the answer. From 0 to a. Got it? What do you think it would be if it was an odd function? You remember what odd functions look like? They're reflected, they say, about the origin. It's a double reflection. It's a reflection over y, then x. So let me show you. Any guess as to what should happen if we integrate from negative a to a? 0. It'll be 0. Watch. Let's look at it. Here's an odd function. So let's talk about first why it's odd. If I were to take this piece right here in blue, reflect it over the y-axis, it would be there, wouldn't it? See my reflection over the y-axis? But now reflect it over the x-axis, and bam, it lands right there, right? So anytime you have a double reflection like that, that's called an odd function. So if you have an odd function, right, if it's odd, and you integrate from negative a to a, again, it has to be from negative a to a, it can't be from a to b, then whatever area you get on the right is going to be canceled out by the area on the left. And so you should always get 0. That's what this is saying. But you have to have an odd function for that to be true. So as a quick example of this, the cosine function, sorry, the sine function is odd, right? That's the sine function. If I do the integral from negative 7 to 7 of sine x dx, my answer is what? 0. I don't have to do any work. All I have to do is say, oh, well, I know this is odd, and that's negative a, and that is A. And so I know my answer is 0. Now, had this gone from, let's say, -7 to 10, then no, that's you don't know, right? You don't know. What would be one way you could find it from -7 to 10? Would you really have to go from -7 to 10? Could you do something clever? Let's say this was a 10. Go what? Just go from 7 to 10, right? So if you wanted to go from -7 to 10, you could already know that from -7 to 7, they cancel each other. So you could just go from 7 to 10, and that will give you the answer. There's a problem in the homework that when you look at it, you're like, shit, I don't know how to integrate that. It's actually impossible to integrate, all right? But just look, it'll go from -a to a, and it is an odd function. So your answer is 0. You don't have to do any work. So just pay attention to that. If you ever see the same limits, like one of them negative and positive, start thinking, maybe it's even, maybe it's odd. Do you all know how to check to see if a function's even and odd? No? Should I review it real quick, or you? Yeah, just a real quick review. Okay. So we'll do these. Okay, even. To check if a function's even, here's what has to be true. When you plug in x, you get the same thing as when you plug in -x. That's what you have to check. For it to be odd, when you plug in -x, it's the same as the original function, but with a negative. So I'll give you an example of an even and an odd and how you could check it. So if I take, for example, the function f of x equals x squared. Now I'm going to give you very basic examples here, okay? If f of x is x squared, how can I prove that that's even? Well, all I have to do is show that this is true, that f of x equals f of -x. So let me plug in -x into this and see what happens. If I plug in -x, I get -x squared. But when you square this, right, the negative is not going to matter because you're going to be squaring a negative, so it'll become positive. So this is also the same as just x squared. And you can see those two are the same, right? F of x equals f of -x. So this is an even function. Now for an odd function, I'll take the most basic odd function there is, x cubed. I could try the same thing. Let me try -x in here. Well, if I plug in a -x, now I know that when I cube a negative number, right, it does not become positive, it stays negative. So this really could be looked at as being negative x cubed. These two are not the same, are they? No. But couldn't you say that this answer is the opposite of that answer? So you could say that negative f of x, which is the original function with a negative in front, these two are the same, right? So now you have that this equals this, which is what the property says has to be true for odd. Now it's a little harder with sine and cosine, because sine and cosine, you just have to know that sine is odd, and you just have to know that cosine is even. Later on, we'll actually show you why it's odd and even using series, which will be kind of eye-opening once you see it. Okay, so back to the properties. Oh, that's it. That's it for the properties. All right. Okay. All right, so now, I mean, theoretically now we have all these techniques. We know how to find antiderivatives of very complicated expressions. And now if we add numbers, we know how to use a fundamental theorem of calculus to get like areas. We can use a couple of these properties if we need them for breaking it up, you know, if we need to break it into multiple pieces. And so with all that kind of like established now, we move into the next important section, which is 6.6, which is titled Improper Integrals. And these are some interesting things here. Let me close this out. Improper integrals. All right, so up to this point, everything we've looked at has been, make that a little bigger, has been trying to find areas under curves on closed intervals. So we're starting at A and we're ending at B, right? And we're finding the area underneath that function on that closed interval. Now we investigate areas on infinite intervals, right? And I should have said this, 6.6 is broken up into two types of problems. The first type here, type 1, are called infinite integrals. Type 2 is called infinite integrands. And you'll see the difference once we get to these. But the first one, infinite intervals, saying, hey, look, we've been starting at A and ending at B. Like, why don't we start at A and never end, right? Just let it go forever and see, can we get an answer still? Now that should probably bother you a little bit, because if you think about an interval that maybe goes on infinitely, if we're trying to find the area, then is it possible to even get a finite answer, right? Because you're going forever. So yeah, we'll see, right? It'll depend on the function. So here are the types of integrals we are now going to investigate. There are three types. Within this one type of problem, there's three types of infinite intervals we can have. You can start at A, so like a left endpoint, and go forever. You can have a point B, which is like a right endpoint, and go to the left forever, or you can go in both directions forever. Right, so I'm going to show you pictures of these. This would be an example. Just look at the picture. Don't worry about all this notation. This would be an example of an integral where we start at A and we go to infinity, right? So we're trying to find the area underneath this curve, but we go forever, all right? Now notice the curve it has a horizontal asymptote. So the function is starting to asymptotically approach the x-axis. So those areas are getting smaller and smaller. So the question is, if we could add up those areas forever, would that converge to a number, or would it just become an infinite answer? And it is all going to depend on the function itself, all right? The function will dictate whether or not we have a finite answer or not. All right, the other type, or the other kind of visual, is the other direction. All right. There we have a left endpoint, a right endpoint of B, and it goes this way forever. And we're trying to find that area. And then the last case would be where, you know what, we're like, shit, let's just go both directions forever. Right, like that. Okay. So that's the visual idea of the three types of infinite intervals. Now we need to establish how we're going to do it, right? So how are we actually going to do these? So I'm going to go back up to this first one, and I want you to focus your attention on this right here. I'm going to move all this over to our notes. Okay, so let's look at this. If we want to do an integral that starts at A and never ends, right? Goes out to the right forever. The way we're going to do it is this. And I think this makes sense if you just think about it. We're going to find the area, okay, this integral in blue, right? That right there, that would be the area from A to T, wouldn't it? But see, T, I'm not going to fix T as a number. Like, I'm not going to go from like 2 to 10. I'm not going to go from like 1 to 7. I'm going to go from like 2 to T or 1 to T. And I'm going to do the work and I'm going to get an answer. And whatever that answer is, it's going to have a T in it because I'm going to leave that T as a variable. And then at the end, I'm going to take the limit and let T go to infinity. And what it's going to do is drag that area out to the end. That make sense? So all these infinite intervals involve limits. And if it involves limits, that means you have to go back to Cal 1 and you have to remember, how did we do limits? Because in Cal 1, there's all types of limits we ran into, right? You know, 0 to 0, infinity over infinity, 0 times infinity. 0 to the 0, 1 to the infinity, all these weird indeterminate forms, L'Hopital's rule, all this, it's all about to present itself again to you, okay? So here we go, all right? That's the idea here. So let's do one like this, and then we'll look at the other direction, then we'll look at what if it goes both ways. All right, let's do our first example here. Let's take a function I think we can all like relate to. The very, very common function or easy function, f of x equals 1 over x. Okay, let's take a look at that function. We should all be familiar with this function, the way it looks. We should all know it does something like this, like that. That's a very rough sketch of what it does, right? And here's what I'm interested in. If we start, let's say, at 1, and we go out to the right forever, I'd like to know what that area is. Okay, that's my question. So what is your instinct telling you? Should that area be infinite or finite? What do you think? Infinite? I mean, it seems like, I mean, you have area, right? The further out you go, I mean, the more you go, the more area you have, right? You keep adding to the cup, you know? All right, let's see. Let's see what the calculus tells us happens here. So in terms of an integral, here's what we have. We have the integral, we're starting at 1, we're never ending, so we're going to infinity. The function we're integrating is 1 over x dx. Now, according to the definition that I just had up on the board, which I will, let me grab just that definition right here. I'm going to grab just this. You know what? Hold on. I don't want all that highlighted stuff here. Okay. According to the definition of this improper integral, what I need to do is rewrite this as a limit. And I'm going to let t go to infinity. And the integral I'm going to do now goes from 1 to t. And the integrand, the function I'm integrating, is 1 over x. So everything I'm putting in this bracket, you don't need the bracket, but everything that's in that bracket is something that we know how to do. That is a definite integral. The only difference is instead of using 2 numbers, I'm using a number 1 and then a variable t. So using the, let me rewrite the limit because I'm not done with it. Using the fundamental theorem of calculus, this right here, I need to find the antiderivative of natural log of x. I mean, sorry, of 1 over x, which is natural log of x, right? It should be natural log of absolute value of x, shouldn't it? Now, I'm not going to put the absolute value. Why do you think I'm not putting the absolute value? I could, but why do I not need to? Can anyone tell me? It's actually
Never negative.
we're not negative, right? What are our values of x ranging from? 1 to infinity, right? So I never have a negative in that natural log. The reason you need the absolute value when you're doing indefinite integrals is because you don't know what x is, right? So you have to have the absolute value there. Here, we know we're looking from 1 to infinity, so x will never be negative, so we never have to worry about the absolute value or getting negatives inside the natural log. So I'm just going to put natural log of x. I'm going to go from 1 to t, right? 1 to t. All right. This is equal to the limit as t goes to infinity. And now, again, I have to use fundamental theorem, so I'm going to just plug in. I'm going to subtract, see what happens. So I start by plugging in this first one, t. I get natural log t. And then minus, I plug in 1, natural log 1. I hope that we all remember that the natural log of 1 is 0. Right? Natural log of 1 is 0. And so what I'm left with is this. Limit t goes to infinity of the natural log of t. That's all I'm left with. So now I need to do this limit. This is a cal1 limit right here. It's saying, hey, look, everyone, look at the natural log function. Let t go to infinity and tell me what happens. So I think you would have to know what the natural log function looks like. Natural log looks like this. This is natural log of x, right? That's what it looks like. So here we're using t instead of x. But if you were to start to go out to the right forever, right? Just start going out to the right. What is the natural log function doing?
Going up forever.
It's going up. Now, it doesn't go very fast, but it does go up, right? So the further to the right you go, the bigger it gets. So this is approaching what? This is going to infinity, right? It's going to infinity. So our answer, what's our answer going to be then? Because we were asking, what's the area under this curve, right? From 1 to infinity. Our answer is infinity, right? That's what we're getting in the limit. So what do we say about that area, right? We have terminology here that we need to establish. If you get, so let me say it this way. All of these problems, these improper integrals, all involve limits, don't they? And limits either exist or don't exist, right? If it goes to infinity, then basically this limit doesn't exist. I mean, it does, it goes to infinity, but the limit, whenever you have infinity, in order for a limit to exist, you have to have it go to a real number, okay? To a real fixed number. So when it comes to areas, here's what we'll say. If you get infinity, right? Or negative infinity, or just does not exist, period, if you get that, then we will say, oh, thank God, that's not. Okay. Freaking me out. Okay. My wife is having medical issues. Last Monday, she called me in the middle of class. I had to leave and she went to the ER and she woke up today with the same symptoms. So she's hoping it passes, but I'm like, call me if shit hits the fan. So that wasn't her, thank goodness. Okay. All right. So if you get infinity, negative infinity, or the limit doesn't exist, any of those three, we will say that this integral diverges. Diverges. All right. That's new terminology. I'll put the note up here in a second. That's the new terminology. So when we come up here, this right here, this integral diverges. The way that I want you to think about diverges is not that we're saying that this area becomes infinite, which it is. It is becoming infinite. But diverges means just that it does not converge to something. So divergence is basically not convergence. In this case, yes, the area becomes infinite. All right, let's try another one, okay? How about instead of that, why don't we do f of x equals 1 over x squared? Yes. Diverges. Mm-hmm. Yep. Now this one, if we graph it, it looks similar. The right side does this. The left side does this. So it's a little different, right? But we have the same thing happening here, that if you were to start somewhere, like let's say 1, and I ask you for the area here, the area is getting smaller and smaller, right? But it goes forever. So, you know, your instinct again may be, yeah, we should diverge here, right? We have an infinite amount of area as we go to the right. It's not going to happen. Watch. If we do this integral from 1 to infinity, 1 over x squared dx, the definition says that this turns into a limit as t goes to infinity of the integral from 1 to t. And I'm going to rewrite that as x to the negative 2 dx, only because what I'm about to do is do an antiderivative. And 1 over x squared, that's not natural log, right? So this we're going to have to use the power rule on, aren't we? The power rule to do this one. So this should be limit t goes to infinity. Now I'm going to do the bracket again. I don't need it, but the antiderivative of x to the negative 2 should be negative x to the negative 1. Believe that? I hope you're okay with that. And we're going to evaluate that from 1 to t. So my daughter's in 7th grade, and I was arguing with her last night about solving linear equations because she's solving linear equations in pre-algebra. And she's so used to doing multiplication with the little cross, and she's just now they're, teaching them with the dot and stuff. So I'm telling her not to do that. I'm trying to convince her to curl her t's instead of making them look like t's, because t's look like plus signs, right? So I'm curious how many of you curl your t's. That's something I didn't do until I kept doing more math.
Yeah.
I better curl my t's. And then the other thing I started to do is I started to strike my z's, because my 2's and z's look too much like each other. So when you start getting really complicated expressions, taking a z and striking it will help you. Curling the t helps. There's other little things like that come up. So I'm going off topic, sorry. Okay, so here's where we are. Now I'm just going to use the theorem. No limit yet. I'm just going to evaluate this at the 2 endpoints. So I forgot my minus sign. I plug in t first for x, right? So this becomes negative t to the negative 1. And then when I plug in 1, I get negative 1 to the negative 1. That looks weird. Doesn't that look weird? Negative 1 to the negative. Maybe we should have done this. Maybe instead of writing that, maybe we should have all just realized that that's negative 1 over x. Right? I think that's better to look at, don't you? Now, I did that on purpose. So instead of looking at this, let's just write on the next line so that we're all clear that this is negative 1 over t, then minus negative 1 over 1. Okay. Now, let's do this right here. This is negative 1. So we're subtracting negative 1. So that's plus 1, isn't it? So this is limit. I'm almost ready to do the limit. We've got negative 1 over t plus 1. There we go. Now let t go to infinity. Right? Let t go to infinity. Do y'all see what happens here? You have a fixed number on top, right? Negative 1 is fixed. Your denominator starts to blow up. That fraction becomes small, right? And that heads to 0. So this basically vanishes in the limit. This right here will head to 0. And then I still have plus 1, right? So my answer is what? 1. Which means that this converges. Converges. Because we got a nice finite number. Now we have to make sure we understand what this actually means, all right? So I think what I'm gonna do is I'm gonna go to a graph to help us see this. Whoa, okay. So if I graph 1 over x squared, okay? If I graph that, and let me do one more graph here. Okay. So if I graph this, and I start at 1, and I start taking this area under here, and I keep going. Here's what I can tell you. If you go out as far as you want, okay? And stop wherever you want. And here's what I'll tell you. Your answer is less than 1. Okay? The further out you go, the closer you'll get to 1. Right? But you'll never surpass 1. If you went out to 1 billion, I promise you that area under there would probably be like 0.999999. Okay? But it would be less than 1. If you could go forever, if it was somehow possible for you to go forever, that would be equal to 1. Equal to 1. If you could go forever, which you can't go forever, but theoretically, if you could, that's what the number 1 is. That's kind of weird, right? The number 1 is the area underneath that curve from 1 to infinity. Strange. Do you not find that strange?
Yeah.
You're okay with that? To think
This
of,
is gonna-
something simple like 1. I can convince you maybe another way. I mean, we're done with this problem. Yeah, I'll talk about the other thing later. So I'm going to graph on this also, just so you see it. I'm going to graph the problem we did before this, 1 over x. Okay, 1 over x is in the green here, right? The area under the green one from 1 to infinity, that diverged. So what I'm saying for the green one is this. If you go out, okay, you go out and stop somewhere, whatever answer you get, I can always get bigger than that. So if you say, well, look, the area under the green one, if you go forever, it never gets past 100. I could go far enough that I could make it go past 100. You say, well, no, the area under the green will never go past 1,000,000. I can go far enough to get past 1,000,000. Does that make sense? There's no number you can give me that I can't make the area go past your number. But with the red graph, there's no number you can give me. I mean, nothing that you can do to make the area go past 1. And it's all based on what? I mean, what can you tell? What's the major difference between these two graphs? They basically behave the same way. So why is one acting one way and the other one's the other way? What do you think that's dictating that? I mean, there is a difference between them.
What value it's approaching?
Well, they're both approaching 0, right? The functions are both asymptotically approaching 0, right? So on one of them, the area is unbounded, and the other area, the area is finite, right? The green one, the area underneath it's unbounded. The area under the red one is finite. So it's all about how fast they're asymptotically approaching 0. The green one is approaching 0, but not fast enough. The red one approaches 0, but fast. So it's the rate. And what dictates that is the function itself, right? And that's kind of troublesome for us because then it matters, like the function actually matters. It's not enough to just look at it and be like, oh yeah, it goes to 0, therefore the area is going to be finite. That's not enough. You have to analyze it. You have to take the antiderivative. You have to take the limit. Okay? All right. So let's see what else we have on our plate here. What about the other way? You know, there's a slight difference in the formula and the setup, but it's pretty much the same thing. So maybe we should do one of those. Oh, here, look. If the limit exists, we say the integral is convergent. If these limits don't exist, we say the interval is divergent. All right. And when I say don't exist, infinity and negative infinity count as do not exist. Okay, so that's why I like to think of divergence as not convergence. Convergence is it goes to a number, a nice fixed number. Divergence is everything else. Okay. All right. Divergence is not convergence. All right. Anything other than convergence. Convergence is that the integral goes to a finite number. When you take the limit, you get a finite number. Okay, I'm going to give you one. Yeah, let me give you one. Let's see how you do with this one. Okay, you ready? I want you to try and do, this is going to test some of your skills here. I want you to do the integral from negative infinity to 0 of 1 over 1 plus x squared dx. Now let's work on that. You can work together in groups. You can talk to each other. I'm going to give you a few minutes. I'm going to just go call my wife real quick, just make sure she's doing okay. And then I'll come back and see how far y'all have gotten with this. Sound good? Everyone at home, y'all all right with that? Okay.
Suppose so.
I'm gonna mute this just for a moment. I'll be back. Okay. Any progress? Did you all convert it to a limit? Let t go to negative infinity? Integral t to 0 of 1 over 1 plus x squared dx. Does that make sense? Like just following the format of what we did with the last one? Does that first step make sense? How about the antiderivative? Arctangent, you recognize that? Okay, so this should be, y'all can hear me at home, right? We're good?
Yes.
Okay, thank you. So now we have arctangent of t, right? I'm sorry, of x, evaluated from t to 0. Right? Then we continue with the limit. We're not ready to let t go to negative infinity yet. Let's go ahead and evaluate at the two endpoints. So we plug in 0 first, arctangent of 0, and then arctangent of t. Y'all still good with that? Now, we need to know a little bit about arctangent to be able to complete this problem. And this is where things start getting a little bit funky for students, all right? So it all depends on how you look at arctangent. I know the way I look at it, but you know, how do you look at it, right? So the way I think about arctangent is this. I go back to the tangent function. This is what tangent of x looks like. And let's see, pi over. Okay, this is what tan x looks like. Let me zoom out here. Yeah, there we go. So here's tangent, right? That look familiar? That's tangent, not arctangent. If we talk about arctangent, what we have to do is we have to restrict the domain of tangent. And we restrict it between, anyone remember? Negative pi over 2 and pi over 2. Okay, so if we restrict the domain, then we have a one-to-one function. Okay, we have vertical asymptotes at pi over 2, and we also have vertical asymptote at negative pi over 2. Right? You do this in green, make it dotted, green dotted. Okay, so this is what the tangent function looks like. With me? So, arctangent of 0 is saying, when does this function spit out 0? At what angle? Because our angles go from negative pi over 2 to pi over 2. So arctangent of 0 is saying, where does you get 0 here? Which is what? At 0, right? We plug in 0, we get 0. We have an x-intercept there. Understand? So this part is going to be 0, which means now we're looking at the limit as t goes to negative infinity. And the only thing left is negative tangent inverse of t, right? Because that was 0. And now we do a limit. Think about what this is asking you. It's saying if this value of t starts to head to negative infinity, what is inverse tangent of that? So I go back to my graph and I say, okay, well, what that's really asking me is, where does this graph head to negative infinity? Well, it's when you go out the left side, right? This left side, as you go down and down, this graph is headed, right? It's headed down to negative infinity, right? That's where it's headed. Now, what x value corresponds to that? Negative pi over 2. But negative pi over 2 is not in the domain, right? but this is a limit, right? We're saying, what is it approaching? So as your x value approaches negative pi over 2, approaches negative pi over 2, your function heads to negative infinity, which means that the answer to this limit, okay, the answer to this is negative negative parenthesis, what? So what is that headed towards? Negative pi over 2. Another way of saying this is as we head to negative pi over 2, right? As we head to negative pi over 2, the tangent function heads to negative infinity. And so when you put those together, your answer is pi over 2. We have a finite answer. We have a finite answer, which means this converges. Converges. Let's look at the graph of that one. We didn't graph the original function here. I'll go ahead and graph it. It was 1 over 1 plus x squared. There we go. That's the graph of 1 over 1 plus x squared. And we are looking out the left-hand side. So we are only looking from here over to infinity. And what we're saying is if you keep going that way and you find the area, it converges to pi over 2. What type of function is this? 1 over 1 plus x squared. Can you tell by looking at the picture what type of function that is?
Even.
It's even, right? It's symmetric to the y-axis, right? Which means the area on the other side should also be pi over 2. So what if I wanted the area of the whole thing, both sides? It would be pi, right? 2 of the pi over 2s. So it'd be pi. Make sense? All right, now that we're a little ahead of ourselves on that, but let's talk about how we would handle this last case where you go both directions forever. All right. The way we do this, okay, the way we do this, if you want to go from negative infinity to infinity, the way you do it is you break it into two improper integrals. The first one goes from negative infinity to a, and then you take that area and you add it to the integral from a to infinity. And the a that you pick is any number you want between negative infinity and infinity. So what is the most natural number to pick in the middle? 0, right? So it's like you're just going to split it into 2 separate limit problems. So let's do one of those. I'm going to do actually the same function that we just did. I want to do the integral from negative infinity to infinity of 1 over 1 plus x squared dx. So the way I do this is I break it into the integral from negative infinity to 0 of 1 over 1 plus x squared dx plus the integral from 0 to infinity of 1 over 1 plus x squared dx. So the 0 could have been any number I want. I could have gone from negative infinity to 1, then 1 to infinity, or negative infinity to 10, and then 10 to infinity. Up to me. But I use 0 because it just makes most sense. Now, this integral on the left, we just did that problem, didn't we? So I'm not going to redo it. That's pi over 2. And by the symmetry, we know the other side is going to be pi over 2. But I would suggest you do this problem. Okay, like go do it on your own. Find the antiderivative. Take it. It's a limit problem, right? You have to do a limit. You should get pi over 2 here. And when you add the 2 together, you get pi. These types of functions are extremely important. Extremely important. I'm going to try and convince you why. All right. Any questions, though? Before I try and convince you where these come into the real world? Okay, so I'm going to talk about, this is going to be kind of a little bit of statistics. I'm not going to test you on this. It's just, sometimes it's good to see where this stuff is used. So I'm going to talk about statistics. Your background in this will vary. Okay, it depends on what you've seen in your life. So when it comes to statistics, there are two types of variables that we have in statistics. There's discrete variables, and then there's what we call continuous random variables. So discrete random variables and continuous. So have anyone ever heard that before or no? It's okay if you haven't. Discrete and continuous. Okay, so in statistics, there are two categories, right? You have discrete variables, and then you have continuous. Okay, so let me give you an example of these two types of variables. So let's say for discrete, let's say we have a standard, let's just do a die, like a die, right? You're gonna roll a die, right? So let's just take a 6-sided die. You roll it, right? That would be a discrete variable. The reason why it's discrete is because when you roll it, you only have 6 outcomes, right? When you roll the die, you can get a 1, you can get a 2, you get 3, 4, 5, or 6, right? With the die. So I'm doing the dice, we'll say dice, okay? 6 outcomes. Those 6 outcomes are equally likely to happen, aren't they? I mean, if it's a fair, balanced die. So we can create a graph. It's called a probability distribution function. Here's what it looks like. On the x-axis, you put the possible outcomes. Let's say this is 0. The outcomes are 1, 2, 3, 4, 5, and 6, right? Those are your outcomes. On the y-axis, you put the probability of each outcome. So what is the probability of getting a 1? 1 out of 6, right? 1/6. So I'm going to measure up, the height of this is going to be 1/6, which means 1 is way up here somewhere, right? 1 is up there, 1/6 is down here. So the probability of getting 1 is a 1/6. Probability of getting 2 is 1/6. Probability of 3 is getting, right? All of them are 1/6. So the way I'm going to represent that geometrically is this. I'm going to create a rectangle that goes up to 1/6 over and down. And I'm going to start it here at half and end it at 1.5. So how wide is this rectangle? 1. How tall is it? 1/6. What's the area of that rectangle? 1 times 1/6, 1/6, right? I do that for each of these outcomes. 2, 3, 4, 5, 6, right? Each one of those has an area of what? 1/6, right? When it comes to statistics, if you look at all the outcomes, right? What are all the possible outcomes when you roll a die? You can get a 1, 2, 3, 4, 5, or 6. If you add up all of their probabilities, what should it add up to be? 1, right? It should add up to be 1. The sum of all of the outcomes, the probabilities of all outcomes must be 1. You agree? If we do something similar to this, let's take a coin, right? If you flip a coin, right? Heads or tails, right? So if we do it this way, you're going to have heads, you're going to have tails. So we could number it. We could say, heads is 1 and tails is 2, or heads is 0 and tails is 1. Doesn't matter, but we could do the probability is a half. We do a little rectangle. Sorry, those are supposed to be equal. Okay, 2 rectangles where each width is 1. And then the heights are half, so that the 2 areas are half and half. So if you add up those 2 areas, you get 1, right? Okay, and that works for anything where you have a discrete variable. So what would be another discrete variable? What can you think of? How about if I just ask you right now the number of siblings you have, right? The number of siblings you have, right? That would be a discrete random variable. You're either going to tell me 0, or 1, or 2, or 3, right? And so the probability that you have 0 is probably pretty high, right? Let's just draw this. The probability that you would have 0 siblings is probably pretty high, right? I don't know what it is, but it's pretty high. The probability you have one sibling, I don't know. Do you think it's more probable that you have one or none? I don't know. We'd have to do some research, but it's going to be a probability. Remember, a probability is something that, we talk about probabilities before something happens, right? So like if I take a coin right now, right, and I flip it, right, and I say heads, which I ask you, what's the probability that it's a heads, right? You're going to tell me 50%. That's wrong because I've already flipped the coin. It is what it is, right? Before I flip it, we have a probability. After the events occurred, there's no more probability. So when we're talking about the probability of siblings, it's about, we can't go ask you how many siblings you have and then ask the probability. It has to happen before it. So we would have maybe two, I don't know what these are, but would you agree these get smaller though? Okay.
Yes.
Now, do we have a cap though? Do we have an actual cap anywhere? It'd be hard to come up with an actual cap, right? Because I've heard of people who have like 15 siblings, right? So we can't really put a hard cap on this, but here's what I can tell you. The sum of all these probabilities has to be 1. In order for it to be a true probability density function, the sum of all the probabilities has to be a 1. Now, that's discrete. What are continuous random variables? So a continuous random variable would be like that water bottle right there. What is it? How many ounces does it say is in there? What does it say? 16.9. So we have a plastic water bottle, right? Sitting on the table. It says it has 16.9 ounces in there, right? Do you think that it is exactly 16.9000000 forever ounces in there? No, right? There's going to be some variation in there. So if you look at that one, right, that scenario, you have, it says 16.9 ounces. Let's just say 16 ounces to make it easy. You have a bottle that says 16 ounces. So it comes out of the plant. There it is. If we were to open it and measure it with a super precise instrument, what's the probability that it is 16? Well, I mean, eventually our instrument has to stop. We can't get so precise we can go out infinite decimals, right? So would you agree if this is 1 up here, the probability that it's 16 is not 100%, right? It's got to be lower. Now let's say here's 17 ounces here, and let's say this is 15 ounces. It can take on all these values in between, right? Can't it? It's not like the die where it's 1, 2, 3, 4, 5, 6. It's not like the coin, heads or tails. It can have any value in between, right? That is called a continuous random variable. So we need a probability assigned to each value, including all the little stuff in between, which means we need a probability for that single value. And it can't be 1, right? 1 would be 100%, which can't happen. But as we move to the side, each of these probabilities should be a little bit lower because, well, unless our machine sucks, right? We should have a machine that's putting out pretty close to 16. And if we get down here, let's say this is 0, what should happen here is this should drop down like this to 0, right? Like that. And then over here, it should also do the same sort of thing, like this. And what we need is that the area under this be 1, right? You need that the area under this be 1. So the most famous one of these is something I know you've all heard of. The bell curve. Everyone's heard of the bell curve? Somewhere in your life, I'm sure you've heard of the bell curve. The bell curve is what we refer to as the normal distribution, the standard normal distribution. And look at it. It's a nasty looking function. Okay, 1 over the square root of 2 sigma pi e to the negative x minus mu over squared over 2 sigma squared. This right here is a very, very nasty looking function, but it is a very important function. Here's what it looks like graphically. Now the mu and the sigma, I can change. And what it does is it moves this graph left and right. And it moves this out and in, okay? And the graph goes in both directions forever. So the standard bell curve or the normal distribution is like, I like to think of it as like, how tall are people, right? You have a lot of people that are going to be in this like one region. Probability of being a certain height is really high, but then it starts to drop off. You know, you have some short people, you have some really tall people, right? Most people are in the middle. When you think about grades, right? You give a test, you hope that everyone's in the middle, like you just have the kind of like this middle, then you have these outliers, right? People who really get it and people who are really struggling, right? This is our standard normal distribution. If we were to find the area under this curve, it would be 1. 1. That's what makes it the normal distribution. The area under that is 1. Now you would have to integrate this function. Now that integration is not easy. Actually, it's impossible to do by hand. We have to use series to do that, but it's one of the most important functions in statistics. All right. So here I had the computer do it. I had the computer integrate this from negative infinity to infinity of that big, nasty, ugly thing. And you see the answer is 1. The sum of all probabilities is 1. Okay. Now, a nice formula. We're going to show that this formula is true now. Show that if we take the integral from 1 to infinity of 1 over x to some power, that it's divergent whenever p is less than or equal to 1, or convergent if p is greater than 1. So before I do this, I need to convince you of something, just to make sure that we're all on the same page with something. All right, let's say that I have some number, all right? Let's say r. And I raise that to, how do I want to do this? I raise that to some power, p, right? And I let I'm trying to think of how I want this. You know what? Let me do this. Let's address this when we get to it. I think when we get to it, we can handle it. I think doing it right now, you're gonna be like, why are we talking about this? Okay, let's just do this problem. We have the integral from 1 to infinity of 1 over x to the p. First of all, that's an improper integral, right? So we're going to change it to a limit. We're going to let t go to infinity. And we're going to go integral from 1 to t is 1 over, integral is 1 over x to the p dx. Now I need the antiderivative of 1 over x to the p. So to help you with that, I'm going to do this. I'm going to rewrite it as x to the negative p dx. And then I'm going to use the power rule. What is the antiderivative of x to the negative p according to the power rule?
Negative x to the negative p plus 1.
Okay, so you're going to take this power, right? You're going to add 1 to it, right? So we have to have x to the negative p plus 1. Okay, I agree with that. What has to go out front?
It'll be 1 over negative p plus 1.
1 over negative p plus 1 comes out here, right? That should be the antiderivative. As long as what? There's one condition where this doesn't work.
P can't be 1.
If p was 1, right? If p was 1, this doesn't work. So I'll put that at the end here. It's this evaluated from 1 to t, right? Like this. Now this is the case if p is not equal to 1. That's the case, right? As long as P is not 1, this formula should be true, right? Do y'all see if we plug in 1, what happens? You get division by 0 here? Okay, we will have to come back and look at this. Like, what if P was 1? We will look at that, but let's just assume right now that P is not 1. Okay, so now what we do is we start plugging in, right? So limit T goes to infinity. We have two things we have to evaluate here. All right, I plug T in first for X. -1 over negative P plus 1. T to the negative P plus 1. And then on the other one, I plug in 1 for X. So 1 over negative P plus 1 times 1 to the negative P plus 1. Now, what is 1 raised to any power? This should just be 1, right? So we have, I'm going to cheat here. Copy this, paste it. So this is just 1 here. So I don't, well, I'll put the 1. Isn't this on the right-hand side just some number? Isn't this just something, because T is going to infinity, right? So T has no impact on this answer. No impact. In fact, you could say that this is just equal to, well, we'll leave it. Okay, so the question is, what happens when T goes to infinity? So if T goes to infinity here, so right now I want to focus all my attention on this limit. I'm going to ignore this right here. That's just a number. What is the limit as T goes to infinity of T raised to the negative P plus 1? So think about this. P is fixed, isn't it? P is a fixed number. It's not 1. It's just a number. And T is going to infinity. So if this gets bigger, right, and bigger and bigger and bigger, what happens to this limit? It gets bigger, right? Well, maybe. It depends on P. Think about this. So right now, what if P can't be 1? So what if P is 2? Think about what happens if P is 2. Yeah, so like if P was 2, then that limit becomes the limit T goes to infinity, T to the -1, isn't it? Which is really the limit as T goes to infinity of 1 over T. And where does that go? That goes to 0, doesn't it? So if this number right here, if the P was a 2, you would get a negative up here, and then that would drop the T down to the denominator and make it go to 0, right? Would the same thing happen if P was 3? You'd get a negative up there, wouldn't you? So really what's dictating what happens is this right here. If negative P plus 1 turns out to be a negative number, what happens? It'll drop the T to the bottom, right? Then the limit of T to the negative P plus 1 will go to 0. Does that make sense? If that power is negative at the end of the day, then it'll go to 0. Now, what if the power, what if negative P plus 1 turns out to be greater than 0? Now you're raising it to a positive power, aren't you? So T to the negative P plus 1. If this is a positive power, take infinity and raise it to a positive power, it's going to be infinity, isn't it? So that'll go to infinity. So we have two scenarios here. If this turns out to be negative, we're going to have convergence. If it's positive, then we're going to have divergence, aren't we? So I now need to just kind of restate this. This right here really means if I move the P to the other side by adding P on both sides, I get P is greater than 1. So if P is greater than 1, then we get convergence, don't we? We get convergence of the limit. And then this one says, move the p to the other side, that if p is less than 1, we're going to get what? Divergence. And what if p is 1? We threw that case out in the beginning. We threw it out, right? But what if p is 1? Can you all tell me? What if that p was a 1? What are you looking at? 1 over x, right? Which is going to be natural log. Didn't we do that problem already? And what did it do? It diverged, right? So in the case that p is 1, we had divergence. And so we've covered all the cases. And that proves what we were trying to show. And go back to the note. Show that this integral is divergent if p is less than or equal to 1, and convergent if it's greater than 1. So now if you were given a problem like this, this should be easy. If I'm just asking, does this converge or diverge? If I say integral, let's say 1 to infinity of 1 over the square root of x dx. Does that converge or diverge, and why? What's the power on x? 1/2. Is 1/2 smaller than 1 or bigger than 1? Smaller. What happens if it's smaller than 1? Diverges. Do you understand that? You don't have to do any work. This is divergent. So p here is 1/2, which means it's divergent. What if we did this? 1 to infinity, 1 over x to the 8th power dx. P is what? 8. 8 is bigger than 1. This is convergent. Okay. What about this? All I want to know is whether or not this is convergent or divergent. The integral from 10 raised to the 10 to infinity of 1 over the cube root of x. So I didn't say 1 to infinity, did I? I didn't say 1 to infinity. So think about it this way. If we go from 1, right, to infinity for this function right here, what should the answer be? If we went from 1 to infinity, divergent or convergent?
Convergent.
What is p there?
3.
1/3, right? 1/3.
Yeah.
And 1/3 is smaller than 1, right? So that would diverge, wouldn't it? But we're not starting at 1. Where are we starting? Way down, 10 to the 10, which is further down, isn't it? And we are looking at just this part. So the question becomes, if you move further down from 1, does that change the convergence or divergence? What do you think?
No.
No, it doesn't. And here's why. This piece right here, isn't that finite? That's finite. From here to here, that's a finite number. But see, we know that because the p here is is 1/3, we know that this is divergent. It's an infinite area. Yes? So if I take something that's infinitely big and I cut out a finite part of it, take this part out, the rest of it is still infinite. You can remove a finite amount from an infinite something and still have an infinite amount. Does that make sense? So this should still diverge. Would it work the same way if it was convergent? In other words, if I asked you to do the integral from 10 to to infinity of 1 over x to the 4th. This is convergent, isn't it? Which means the sum is finite. And you're going to take out a piece, right? That piece is finite. So if you take out a finite number from a finite number, you should still have a finite number, right? Yeah. So this will still converge. So I'll summarize what I just did with this. Removing a finite amount or finite area from a convergent integral does not change the convergence. Removing a finite amount of area from a divergent integral does not change its divergence. It's still divergent. All right. It's 10:33. So for your homework, all right, what I think you should do is 6.6. Only do integrals. I can bring up the homework assignment, but only do integrals that have on the top and bottom either infinity or negative infinity. So when you're doing, only do those problems. They should be at the beginning of the section. I don't have my book, or I tell you exactly which problems to do. If it has numbers, don't do those. Okay, that'll be next class. All right, and we can talk about the next type. So next class, 6.6, we'll finish off 6.6. Then we'll finally get into the next chapter. You're gonna have limits. You're gonna see L'Hopital's rule in the homework. So I anticipate that you might have questions. You know, just let me know if you do. Otherwise, I think we'll kind of cut it close or cut class early, I guess, 5 minutes early. If you have any questions, I'm happy to stick around and answer. If you want to do another problem, we can do another problem. Did everyone sign in that sheet? You go around. Did everyone get a chance to? Okay. All righty. Y'all have a good day. Everybody at home okay?
Mostly.
Okay.